So first, I was supposed to have office hour today. I had to miss it. I apologize because I did not notify you for that in advance. But I will have office hour to make up for this office hour next Wednesday. I will give you details over the CUNY Blackboard and also from the CUNY course. Okay, so also what I want to let you know is that looks like our final will be on December 16th. That's according to this program, final exam schedule that is on the on Baruch's website. It looks like our exam is on December 16th on Wednesday from 3:30 to 5:30. But we have enough time before the final, so I just wanted to let you know that that will be, I think, that date is still not fully decided because it says it's tentative, but I think it will be pretty much unchanged. I think it will be on December 16th. So in today's class, what I will do is that I will, so as you guys know, so we covered chapter 6. So what I will do today is that I will do some exercises from this chapter. And also I will do certain stuff in Excel and in R. I will not start a new chapter, which is chapter 7, next Wednesday, because I will do a few empirical problems in Excel and in R, and I will start chapter 7 from the next week, next Monday. So, do you guys have any questions before I start?
Yes, I have a quick question.
Sure.
So you said the next office hour will be next Wednesday. That's like next week, right?
No, I said next Wednesday. Today is what? Today is Monday, right?
Yeah.
So, sorry, so maybe I was not very clear. So I meant this Wednesday.
Oh, okay. Thank you.
Yes. But I will give you more details about that exact time. I think it will be before our class. Okay, so let me now copy this problem. Okay, before even I start, it will be very useful if you could log into your Blackboard and then scroll down. Log into your Blackboard, log in our course, scroll down, and then click on week 12 folder. And then there will be, you will see a lot of, not a lot of, but a few documents. One is our code and the others are some Excel files. Those files are, I think, are familiar with you guys because I already uploaded it in some other class. Simply, we did not finish it, and I think it will be very useful if you do some of it today. And so, do you see this? I'm not sure. Okay, I think you see my Blackboard, right? So again, go log into your Blackboard, go to our course, scroll down, and then see week 12 folder, and then download everything that you find in week 12 folder, because I will use that after I solve a few problems from chapter 6. Okay. Now let me share a different screen with you. Okay, now you see my blue screen, right? And let me copy this problem. This is our first problem. Also, I have already assigned chapter 6 homeworks and you had a chance to start working on it. If you did not, it's fine because, as you know, I always extend deadlines. But after I solve some problems, you may find it easier to work on that chapter 6 problems. Okay, so here we have,
Professor, I have a question.
sure.
Are we going to be expected to use R or R Studio during the final?
No, so I've never used it. But the thing is, you guys did really well. In the second midterm, you did outstandingly well. That's great because I think I had pretty sophisticated exam. It was not very easy unless you knew how to do it, I think. And but you did really well. So I may have to slight, slightly, at least slightly increase the difficulty of the final. But I'm still not thinking that I will include questions about R in the final. But the thing is, R very much simplifies things and also very much shortens time that you may consume on a problem. Because as I'm not sure if you guys remember, but in Excel, you cannot, when we need to test the hypothesis, we need correct estimated standard errors, right? And you can, of course, calculate if you have a bivariate model, for example. You can calculate estimated standard error or estimated standard deviation for the test statistic, but that is really, really time consuming. And another option is to use R because Excel does not correct for heteroscedasticity. And if you remember, heteroscedasticity is a problem because that means, first of all, that means that the variance of the error term or the disturbance is not constant. That's a problem because when there is heteroscedastic disturbance, that affects the estimated standard deviation of the test statistic. So the estimated standard deviation of the test statistic has to be calculated in a certain way, right? And so Excel does not have a built-in function that automatically corrects for the heteroscedastic disturbance. So therefore, Excel does not give us, there's no way in Excel, there's no built-in, there's a way you can calculate every term of the expression, everything yourself, and then you get the answer. But as I said, there's no built-in function in Excel that calculates that gives us heteroscedasticity corrected for past estimated standard errors. Guys, am I clear? All of this will be clearer when I do the problem, right? So I'm planning to do it not next, but this Wednesday when I'll, as I said, I will solve a few empirical exercises in class. Today is just the exercises from this chapter, as you see. Then I will do a few, then I will do some R, some Excel, but next class, which is this Wednesday, will be entirely solving empirical problems from the homeworks. Okay, so again, if you guys have any questions, please stop me at any time. Okay. Also, please download the Excel files and also the R code that I said in the beginning of this class, right? For that, just go to the course, scroll down, you will see week 12 folder and then download everything that you'll see there. So, so here we have this model. Let me change the color because I think that will make our lives easier. Let me take, say, this color. Okay. So we have this model. This is not a line because we have this disturbance term here. So therefore, that's not a line, right? So that actually gives us all of the points in our population, right? And of course, there is a line which we call the population line. And that line is what? Can you, of course you can, right? So that is expectation of y, I, conditional on all of your x's. That will be x1i, x2i equals beta 0 plus beta 1 times x1i plus beta 2 times x2i. Nothing very, very difficult. We know this already. Okay, so the question is, what is the expected change in y if x1 increases by 3 units and x2 is unchanged? Let's do this. So initially we have this, right? But then we have a change in x1i, right? So that means that we will have different. So if there's a change in x1i, then it will have different value on the right hand side, right? So then let me call this e, yi, x1i, x2i. But let me call this whatever. Now, what? Let me say this is, let's say, second, because there is a change. It's not a square, it's just something else after a change. So then I will have here beta 0 plus beta 1 times x1i plus 3, and then plus beta 2 times x2i. And then we want to see what's the expected change in y as a result of this, right? So for that, we will just subtract, let me call this starting or initial, let me call this 1. So the change, expected change in y, I will call this, whatever, I will call this delta, stands for change. Delta expected in y, given that we have x1i and x2i, is equals what? That's the new thing minus the initial, right? And that is equal, so just take this and subtract from this that, right? And after you rearrange stuff, we will see the result is 3 times beta 1. Okay, now there's a similar question. Now if looking at this expression, guys, can you tell me what will be the expected change in y when x decreases by 5 units? Guys, so do you guys hear me well?
Yeah.
Yes, sir.
Perfect. So I just want to double check because I want you guys to be involved. So what do you think? So similarly, what I did, what do you think will be the expected change in y when x2 declines by 5 units? It will be minus 5 times beta 2. Right? Today I don't. Okay, I don't have my mouse. And then just using my hand. That's why it is really too difficult to write. So the change will be what? It will be minus 5 times beta 2. And then lastly, what if now both x1 and x2 change? What if now if x1 goes up by 3 units and x2 goes down by 5 units? In that case, the change in expected y will be 3 beta 1 plus, 3 beta 1 minus 5 beta 2. And it is very similar to what I did just a few minutes ago. Okay, so to understand this better, you can just take a look at what I did here, and then you can apply that reasoning to the next two questions, and you will see the result is minus 5 beta 2 and plus 3 beta 1 minus 5 beta 2. Okay. Now let me do another problem, which is 6.5. Let me copy. So first of all, when you see the estimated model, please make sure that you understand the variables. More specifically, that you understand what are the units of measurements of each of these variables. Okay, so everything should be given in the problem, right? So and we see that first of all, the sample size is 220, and that's large enough, right? So because that's greater than 120. And then we have all these variables and their units of measurements. So price is measured in thousands of dollars. Bedroom, BDR, that's a variable that stands for the number of bedrooms. So therefore, let me ask you, is bedroom a binary variable? It's not, right? So it's just a number of bedrooms. It can be 5, it can be 10, it can be 15, right? But it's not, doesn't really take only two values, because we know that a binary variable, or in other words, a dummy variable because dummy and binary, those are the two names of the same thing, right? That stands for a situation when we have a variable that only takes two possible values. Bath, that is just a number of bedrooms. Age size is size of house measured in square feet. L size is the lot size that is measured on, again, square feet. Age denotes the age of the house. Poor is a dummy variable, right? See, that is a dummy variable or a binary variable. It only takes two values. One, if the house condition is poor, and zero otherwise. If the house is in a good condition, then this poor variable will take value of zero. And we have this estimated model, right? What is the first question here? Okay, I have to copy this. Okay, so now I think we are fine. First, okay, probably I have to close this and open again. Hopefully this now works. Okay. A. Suppose a homeowner converts part of an existing family room in her house into a new bedroom. What is the expected decrease in the value of the house? So when you look at this estimated model, so what do you think is the answer here? So when this person converts part of the existing family room in her house into a new bedroom, that means that there is one additional bedroom. So that means that here we have bedroom plus one, right? So the model otherwise will be the same. Simply for bedroom, now we will have bedroom plus one, and that will result in the change in the house price, the estimated house price. So and that will be equal to 23.4 $1,000, right? Why? Because, as we already said, house price, where is it? Here. House price is measured in thousands of dollars. Or you could convert this into dollars, and that will be 23.4 times 1,000, or $23,000. So be careful. What is it that the question asks? Sometimes the question may ask you, give me the answer in thousands of dollars, or it may also tell you that give me the answer in dollars, not thousands of dollars. B. Suppose a homeowner adds a new bathroom to her house, which also increases the size of the house by 100 square feet. What is the expected increase in the value of house? Okay, again, since the homeowner adds a new bathroom, there is a new bathroom, so that means there is one additional bathroom. So here we have bathroom plus one, right? 23.4 times 1 times bathroom plus one. And but also we have a change in the house size, right? So which is, first of all, what is the units of measurement of house size? House size is measured in square feet. So that's great. So because of that, we will have here H size. You can simply add 100. Why? Because it says there is an increase of 100 square feet. And then also we know that house size is measured in square feet. So you can simply write house size plus 100. And of course, it will be multiplied by 0.15 and 6 plus 0.15 and 6, right? And then, so this will give you guys the estimated change in house prices. What house price will be what? 23.4. Can you give me the units of measurement? 1,000 plus what? Plus 0.156 times 100,000, right? Okay, so that means if you want to write this in dollars instead of thousands of dollars, then it will say 23.4 times 1,000 plus 0.156 times 100 and then times 1,000. Oh, 1,000. And that equals to $39,000. Okay. That's the answer. If the question asks you to give the answer in thousands of dollars, then the answer will be this, 39,000. This is very easy, but still needs some thinking, right? What is the loss in the value if a homeowner lets his house to run down? So that means like it was in a good condition, that the owner allows the house to deteriorate, to become poor, in a poor condition. So I don't know why, but the question is not why, the question is what happens, right? Okay, so we see that here is this variable poor, that's a dummy variable. When poor is 1, that means that when poor is 0, that means the house is in a good condition. But then suddenly the owner allows the house to be in a bad condition. So that means that the variable poor now takes value 1. It was before, so poor equals 0 before, 0 before. And now this is part C of this question. And now poor equals 1. This is now. So, and then you just see what happens. Everything else stays the same. What happens to the estimated house price? The estimated house price declines by $48.8 thousand. Or if you want to answer in dollars, there will be percent decline of $48,800. The last part is to compute R squared of this model. And first of all, what do we have, right? So, okay, I'm going to calculate R squared, but do I have enough information? So, okay, we see that we have adjusted R squared. So we know that in this problem, it is given that from this problem, that adjusted R squared equals 0.72, right? 0.72. And okay, sorry, 0.72. But the question is, what is R squared? That's a question. Okay, so we know the expressions of R squared and adjusted R squared. And those relationships, those expressions allows us to write the relationship between R squared and adjusted R squared is what? Adjusted R squared equals 1 minus n minus 1 time divided by n minus k minus 1 times 1 minus R squared. Or you can flip this and we will see that R squared is equal to 1 minus, now n minus k minus 1 over n minus 1 times 1 minus adjusted R squared. What do you do next? You just plug in the numbers. So we know that R squared will be what? 1 minus, what is the sample size? We know that the sample size is 20. What is k? So 220. When you look at this estimated model, sorry, what is k? Can you tell me?
Would it be 6?
Let's see. 1, 3, 4, exactly. So that is 6 because we have 6 independent variables, right? That's exactly right. And so therefore, now we have 220 minus 6 minus 1. This 1 stands for the number of intercept. Number of intercept is always 1. Minus 1. Then times 1 minus 0.72 squared. This will yield 0.72. Sorry. R squared is what? R squared, that's 0.72. So this is nothing. Forget about this. This is already R, adjusted R squared. So then you will get this answer. Now let's do another problem. That's 9. Okay.
Professor, can you please scroll a little bit up?
Sure, sure. Give me a moment, please. I'm copying something. Yes. Scroll up, right?
Yes, please.
Here.
I'm looking for the part C.
Let's see. Part C is, I think that's part C. Let me go down.
Thank you so much.
Okay. So now let's do another problem. That's our next problem. So we learned what it means, what the omitted variable bias mean, right? And we also know when it occurs. So this question says that, so we have 3 variables, 1 dependent, yi, and 2 independent variables, x1, x2. I clearly stands for the observation, right? That can change from 1 to whatever the sample size. And then that satisfies the assumptions, certain assumptions that we know. And we are interested in beta 1, the causal effect of x1 on phi. Suppose x1 and x2 are uncorrelated, right? And then you estimate beta 1 by regressing y on x1. So that means that you exclude x2 from the model. So does this estimator suffer from the omitted variable bias? Can you tell me?
No,
Why?
because the two variables are not correlated.
That's exactly right. So we know that for omitted variable bias, to occur, the condition is what? That you omit a variable that, so Can be for whatever reason. Maybe you omit a variable because you don't know the variable. You might be omitting a variable because you cannot measure it well. Or maybe you cannot measure it at all. Maybe there's no data on that variable. But okay, so if you omit a variable that is not correlated with either, meaning any of the included variables, included independent variables, then there is no problem. Omitted variable bias only happens when you omit a variable that is correlated with at least one included independent variable. Why? Because what's the assumption that we have? What's the key assumption, right? The key assumption for the OLS estimators to be good, and we already know what we mean by a good estimator, right? An estimator that is unbiased, that is consistent, that is efficient is a good estimator, right? And the key assumption is what is why does not work? The expectation of UI conditional on x1, I, x2, I. That should be 0. If you have only one variable in the model, then that should be that is 0, right? Okay, let's say you also know there is a variable x2i, right? Okay, if there's a variable x2i that affects your yi, right? And if you omit this variable, that falls into the disturbance term ui, right? Okay, so then x2 becomes part of ui. Yeah, right? And then if x2 is correlated with x1, since x2 is now part of ui, then ui and x1i will be also correlated, and that violates this assumption. And that's why we generate omitted variable bias when we omit a variable that is correlated with at least one of the included variables. So whoever answered this question, you are completely right. So in this case, since x1 and x2 are not correlated, there's no omitted variable bias. Whether you omit x1 or x2 from the model does not really affect your the estimators, the biasness of the estimators. Both cases, the estimators will be the estimator of beta 1 will be unbiased. Okay, so that's good. Now I will do the last problem that I wanted to do. I think pretty quickly, and then I will do some Excel and some R. But as I said, the next class, which is this Wednesday, will entirely be dedicated to solving some empirical problems from the homeworks. And of course, clearly we will be using R, sometimes Excel. Let me now copy another problem. Okay, that's this problem. Oh. Guys, are you with me? Are you following or?
We're following.
Okay, good. If I'm going too slow, just let me know. So this is the last problem that I will do today, and then I will do some Excel and that. Okay, so and please download whatever I said to download from the CUNY Blackboard. That was I said. Download. Go to our course. Scroll down, see week 12 folder, and download whatever you see there. Excel files and also archive. Okay, so first of all, we see that n is 400. That's very good because we know that sample size is really important. Why? Because when you want to test the hypothesis, you need to know the appropriate distribution of your test statistic, right? Which is in our case either distributed either as standard normal or as student's t. Okay, so we have again 3 variables. Okay, let's go y, x1, x2, and we know that. Okay, guys, something is opening, so I have to close this again and then I open it once again. Okay, now I think so. We know that there's 3 variables y, x1, x2, and we know that variance of ui conditional on x1 I, x2 I equals 4. And also we know that variance of x1 I equals 6. And we know the sample size is 400. Okay, and then let's answer the first question, which is assume x1 and x2 are uncorrelated. Compute the variance of beta 1. Okay, so I'm not asking you guys to remember that expression or to memorize, because there's no point in memorizing this, because why? Because if you have more than 2 independent variables, then these expressions are not even analytically well defined. So there's no reason to memorize anything like this. So now what I will do is that I will give you the expression for the estimated variance of beta 1. So that's denoted by sigma squared of beta 1 hat, and that is given by 1 over n times 1 over 1 minus rho x1 x2 squared times sigma u squared over sigma x1 squared. Okay, what we do now is that we just plug the number c. Um, okay, so this will be equal to 1 over 400 because the sample size is 400 times 1 over 1 minus what will be rho x1 x2, guys, in this case. What is rho x1 x2? Do you remember? That's correlation. This is the correlation coefficient between x1 and x2. But then in part A, what will be rho x1 x2? Will be 0 because in part A we say that the problem states that x1 x2 in part A, the problem states that x1 x2 are uncorrelated, so that's why there's 0 there. And then multiplied by sigma squared of u. Sigma squared of u is simply this, which is 4, and then sigma squared of x1, that's simply that. That's another notation for that, and we get 0.00167. That's the variance of the estimated beta 1. Now let's do part B of this problem. Part B says that now let's assume that instead of 0, let's say the correlation between x1 and x2 is 0.5. What's the new result for the variance of the beta hat 1? So it's very simple because we already know the formula. That's the expression, right? 1 over 400 because the sample size is the same, and then 1 over 1 minus 0.55, right? And that's multiplied by, this is 0.5, and that's multiplied by 4 over 6, and that's equals to 0.0022. And the last question is comment on the following statement. So, guys, when there was no correlation between x1 and x2, we had that we see that the variance of the estimated beta 1 is this, right? But when there is some correlation, when the correlation between x1 and x2 is not 0, what happens to the variance of the estimated beta 1? It goes up because 0.0022 is greater than this, right? So that's really a more general result. So which I'll state here. So we can make a more general statement that the larger the variance, sorry, the larger the correlation between x1 and x2, the larger the variance of beta hat 1. Is this a good thing or a bad thing? Guys, this is a bad thing because what is beta hat 1? This is what? An estimator of beta 1, right? Okay, and that means that we want to have an estimator that has a lower variance because that means that it is, first of all, we want to have an estimator that is unbiased, which is it is centered on beta 1, like this. This is beta 1, right? We want the estimator to be centered here, but also we want an estimator that has a lower variance, like this. This will be much better estimate. This is better. Let's say this is 2. Let's say this is 1. 2 is better than 1, right? Okay, I will come back to this later, but that's all I wanted to solve today from chapter 6. Now I will start doing certain things in Excel. Okay, so guys, let me ask you, up until now, how are we doing?
Good.
Perfect. Now, did you guys manage to download what I said to download? Because it will be useful for you guys. You don't have to, but it will be, I think, useful to do it. Okay, so let me now open another file. So guys, please open CA Schools. CA School copy, that Excel. And click on the first worksheet. You should be seeing this.
We still see your blue screen.
I see. But if you clicked on CA School copy, and if you select the first, which is the first worksheet, CA School, then you'll see this, right? Then scroll to the right. We have all these data. We have 420 observations, because if you scroll down, you'll see that the last one is, the last row is 421, and the first row is just titles. So we have 420 observations. So now what I want you to do is the following. Let's copy a few columns. Let's copy test score column, and let's copy SDR. Let's copy average income. Let's copy this LPCT. Let's copy that as well. Let's copy these columns, and let's open a new column. And then let's paste it here. If you do all of this, you have this, right? And now let's run a linear model. So to run a linear model, you need to have, first you need to have data analysis toolpath added to your Excel, which we already did before. So we can simply go to data and then data analysis. And then we can choose, we need to choose regression. And okay, first we need to input our dependent variable, which is test score. Let me do it. Okay, so that's it. And then we need to input all of our independent variables. How do you do that? You just select all of them like this. Okay. But then if you notice, I have also selected the titles of this, right? Columns. So that means I have to check labels, and then I will just click OK. And then you get this output. So if you did everything right, you should be also seeing this output.
Sorry, I have a question. Which one is X exactly and which one is Y?
The
Or
first,
are they both?
no, the first one. So you have to in Excel, you have to order your variables. The first always should be Y. But the thing is, not really that much necessary, because as you remember, the window asks us, right? So input Y range, input X range. Do you remember?
Yeah, I see that.
You see that?
So which one do I put in for X and which one's Y? So
I
like
see. Test score. Test score will be your Y, our Y, and all the others are our X's, X1, X2, X3. But the thing is, you have the order is important because you know, my variables were like, where is it? What's this, right? So do you see? Test score is dependent, but then I selected all of the independents, right? And I input all of them there.
yeah, like why is it all copied?
Oh, I don't have to.
All of
Yes.
that's Y?
No, I don't have to. So let me do it again then. So let's go to data. I actually selected them individually, but let me do it again. So you go to data, and then you see this data analysis, and then you select
Regression, yeah.
yes, and then you input Y range. I already did it, so let me clear. So then you click here, and then you input Y range, which means that you simply input the first column. But the first column not entirely, just the values, right? Okay, so that's the Y range. And then you need to input the X range. But here we input all of our X's. And then if I select all of them, that automatically assumes that the first X or first independent variable here is SDR.
Yeah, that's what I'm confused.
Right. The second is average income. The third is
I'm like
ELPCT.
confused as to what to put for X.
But now we understand, right?
Yeah, but what is X? Those three? X is STR, average income, and LPCT.
This is English as a second language.
Oh.
Percent of those students whose English, for whom English is a second language. This is average income. This is student teacher ratio.
Right. So those are all going to be X.
are going to be x's, but the thing is, which one? X1, X2, X3. So you have to be careful because, I mean, if I do it this way, right? If I have this ordering, if you want to get the same results, then you have to maintain the order because in my case, X1 is SDR, X2 is average income, X3 is ELPCT, right?
Okay.
Right. Okay, and then check labels, and then okay, and then you will get this outcome, right? The last two columns are nothing. You can delete because as you see, so these columns here are just the repetitions of the last of these two columns, right? Do you see that? You don't need it. You can just delete. You don't have to delete, but I usually delete because why do I have? Should I have anything I don't need? Okay, so these are our estimates, right? So what are our estimates? These are our estimates, right? Are these estimates good? Can you tell me?
Yes.
The estimates are good. Okay, that's correct. These are what?
Not correct.
Very good. Why? Can you tell me?
Mm,
Because it is very unlikely that the disturbance is homoscedastic. It is very unlikely. Okay. For the most of the cases, the disturbance is like for the absolute majority of the cases, the disturbance is heteroscedastic. So that means that these numbers are incorrect. What about these numbers?
not
And
correct.
why? Can you tell me?
I know that we have to use R for the standard error that to find it.
So what is this dot? These numbers, I will explain this very in detail next class, but so these numbers are based on these numbers. How can they be correct if these numbers, these estimated standard deviations are not correct? So guys, please think critically. Is these numbers correct? No, because p-value is calculated based on the t-stats, right? Are these numbers correct? No, because they are based on what? The estimated standard deviation. So all of these numbers are incorrect, which means you cannot do hypothesis test. That's very bad. So what do you need to do is that you have to correct these numbers and then recalculate everything else based on corrected estimated standard deviations, guys. What is this number? Can you tell me? How did we obtain this number? That's that divided by this, right? That gives us test statistic. Okay, so what I said in the beginning of today's class is that there's no way, Excel does not have a built-in function that gives us correct estimated standard deviations. There's no way, unless you calculate everything by yourself, every term in certain expression. Right? But R allows us to find heteroscedasticity, to obtain heteroscedasticity corrected, or in other words, robust estimated standard deviations. That's all for today, guys. I will continue next Wednesday, not next this week, this Wednesday, and I will do certain empirical problems using Excel and R. Thank you very much for being here, and I wish you a good day.
Thank you, Professor. Have a good day.
Thank you, Professor.
Thank you.
Thank you.
Thank you, guys.
Thank you, Professor.
Thanks a lot.